Thanks to Brilliant for sponsoring this video. There's a weird, seemingly unexplainable situation that keeps occurring when driving. A huge pile of traffic comes out of nowhere and suddenly there's a full-on traffic jam. After checking, there's no accident up ahead, nor a roadblock. What's even weirder is that after some time, the jam completely dissipates and the road is back to normal, as if the whole jam wasn't there to begin with. What could be causing such a strange phenomenon? In this video, I aim to introduce the mathematics that allow us to explain such an occurrence, and attempt to reconstruct the tools mathematicians and engineers use to analyze the flow of traffic. Traffic flow theory is the study of different relationships and interactions between vehicles and infrastructure, such as highways, while aiming to understand how such interactions affect the traffic and developing optimal transport networks with efficient movement and minimal congestion problems. It is a subspecialty of the field of mathematical modeling, which deals with translating real-world problems in mathematical terms, in what we call models. This is to provide the use of the tools mathematics offers to give more insight about the problem at hand, reveal more information, and make insightful predictions. Traffic flow models are categorized to many different types. The most prominent distinctions are made between microscopic and macroscopic models, or discrete versus continuous models, and deterministic versus stochastic models. Microscopic models focus on the behavior of individual cars, studying their position and velocities as a function of time, and analyzing their evolution in relation to other vehicles, traffic lights, and so on. In macroscopic models, we look at roads from far enough to the point where the individual behavior of the cars becomes negligible, and the interest lies in analyzing the behavior of the homogenized traffic. In such a model, the traffic becomes analogous to a fluid, and the cars become akin to atoms or molecules. We deal with average concepts that are related to the combined behavior of the cars. For example, we focus on the average velocity of the cars instead of the individual velocity of each distinct car. In stochastic models, the traffic's behavior is not explicitly specified by the model itself, rather it is governed by random variables with specified probability distributions, and we deal with random quantities such as the probability that a car exceeds a certain speed and so on. On the other hand, deterministic models fully determine the behavior and evolution of traffic by the model's laws. Traffic flow modeling has been a field of interest since the early 1950s, where the first microscopic models started appearing. One of the first models were developed by Pipes in 1953. In this model, the velocity of some vehicle is based on the distance between the vehicle preceding it, expressed in this equation, where W here is some velocity function and the delta xi is the difference in positions between two adjacent cars. Several improvements were made to this model by introducing reaction time, delay, and other variables. These are all examples of microscopic models, which are not the type of models we'll discuss in this video. Dr. Traffer has made an amazing video studying a microscopic model for traffic flow, so you can check that out if you're interested. The type of model we'll be focusing on in this video is the macroscopic model, which has been originally introduced in the context of fluid models. By far, the most prominent and most digestible fluid-like traffic flow model is the LWR model, short for the Lighthill-Whitham-Richards model in 1955 and 1956. In such models, quantities are usually described by real, multi-valued functions. This is the model we'll be studying in this video. The main idea of this model is that even though cars are discrete entities, if there are enough of them, and if they're observed from far enough, then these cars will form a continuous density over some region of the road, that is, a local average. How far away we must observe the cars, in other words, the distance along which the average is taken, must be chosen reasonably, for if it's too large, then we lose a lot of information on the behavior of the cars, and only drastic changes are observed. On the other hand, if the distance is too small, then the average will drastically vary by relatively small changes in the car's behavior. The method by which such a distance is chosen is usually determined empirically and heavily depends on the type of model, purposes and goals of the study, the type of road being observed, and even more parameters. But for this model, it can range from a few hundred meters to several kilometers. Let's consider a straight road segment of uniform characteristics. Mathematically, this would be a perfect number line. We require that this road segment have no crossings. That is, the only way to enter or exit the road is from its extremities, which will denote the entrance by A and the exit by B. We'll let the entrance be on the left side and the exit be on the right side. So the driving direction is from left to right. We are dealing with the motion of a number of individual vehicles as they proceed along the straight road, without passing each other. We sum up all of these properties by saying that we have a one-directional, one-lane model with no passing. Now that we have our setting, let's define some quantities of interest. The first and major quantity of interest in this traffic flow model is the traffic density, most often denoted by the Greek letter rho. The traffic density is defined to be the number of cars per unit length of road. This means if we take the unit of length to be, say, a kilometer, then the density will be the number of cars per kilometer. Of course, this clearly depends on two things. One is the locus at which you're calculating the density, as the number of cars varies across the road, and two, on the time which you're calculating the density. Since the cars are moving, naturally, there will not always be the same number of cars in the same spot. And so, the density will be a function of both time and space, which will respectively denote by t and x. So t signifies the state of the road at some point in time, and x represents some point along the road. If you're like me when I was first introduced to this concept when I took my PDEs course, you might be asking yourself the following question. If the density is the number of cars per unit length, and a point is considered to have a length of 0, shouldn't the density evaluate to 0 everywhere? This is a logical question to pose. If you think about it, since a point is considered to be infinitesimally small, then no car can fit inside a point, and the density would always be 0. Although yes, this is true, this remark is missing the point. The density function here works almost exactly the same as a probability density function, in the sense that this function is not meant to be evaluated at a single point, rather it is meant to be integrated along a range of values. If we let capital N denote the number of cars on the road, then we can obtain the total number of cars in the road by integrating rho over the entire road. So n of t would be the integral from a to b of rho of xt, but with respect to x. This is the same way we calculate the probability of a continuous random variable lying between two values. This further highlights the analogous behavior to a probability density function. Without need for a formal argument, since the unit of density is cars per unit distance, by integrating with respect to the space parameter x, we essentially eliminate it from rho, giving us only the number of cars left. If we want to find the number of cars along a section of our road, it suffices to integrate along the endpoints of this section. Or integrate along each connected component and sum the integrals if the section of the road is not connected. Remark that the number of cars is a pure function of time, which is consistent with the fact that cars cannot enter or leave the road except from the endpoints. The next quantity of interest that comes up naturally when studying the flow of traffic is the traffic velocity. Let's denote it by v. This does not refer to the velocity of individual cars, instead it is an average velocity, so the velocity of the moving traffic as a homogenized fluid. Again, the mean velocity of traffic depends on both space and time, so v is also a function of x and t. A more fundamental quantity than the traffic velocity is the traffic flow, or the flux, denoted by q. The flux is defined to be the number of vehicles crossing a certain position x on the road per unit time. So for example, if we take the time unit to be 1 hour, then the flux at some point x is the number of cars crossing x per hour. Of course, this is taken in an average sense. These three quantities are the main object of study in traffic flow theory. And what we mean by studying the traffic is finding an explicit description of the traffic density ρ for all positions x and all times t. These three quantities are linked together in what we call the fundamental equation of traffic flow, which states that the flux is the product of the density and the velocity at each point xt. But where does this come from? Well, let's see if it makes sense first. If we conduct a swift dimensional analysis on this relation, we can see that the units do match up. Of course, let's just assume that we can define a sensible unit that measures cars. If the density is the number of cars per unit, then its unit would be cars over distance, as mentioned before. The unit of density is well known to be distance over time, so multiplying these two dimensions will give us cars over time, which is precisely the unit of the flux. However, this does not constitute a convincing argument, and the question still remains, how do we establish such a relation? The difficulty with showing that this holds is the fact that the velocity varies and changes, as all cars on the road do not drive with the same speed. But we can establish this relation for a constant velocity. Indeed, let's consider a fixed velocity, say v0, and let's ignore all the cars which are not driving in this exact same velocity. The number of cars crossing a section of road, say dx, during a time interval dt with velocity v0, as per the definition above, is ρ times dx. However, since the velocity is constant, we can easily obtain it using the distance over time definition of velocity. This would make v0 be equal to dx over dt, which would say that dx is equal to v0 times dt. On the other hand, the same number of cars can be obtained using the definition of the flux. It would be q times dt. And so we have the equality ρ v0 dt is equal to q times dt. Now we can always choose the unit of time and distance in such a way that dt and dx are equal to 1 here, but we can argue from the arbitrariness of the time interval we took that we can eliminate dt from both sides, and this would give us that ρ times v0 is equal to q, establishing the fundamental equation for a uniform velocity. In order to extend this to any velocity distribution v, we must introduce the density and flux in phase space. I'll denote them by ρ tilde and q tilde, which are defined in the usual sense, so the density and flux, but restricted only to cars moving at the fixed velocity v. This would make ρ tilde and q tilde functions of not only x and time, but of the velocity v as well. So the density of the cars moving between two velocities v1 and v2, so that v1 is slower than v2, would be the integral of ρ tilde between v1 and v2 with respect to v. Now, since our model is unidirectional, velocity as a vector has only one direction, the positive one, meaning we can see it as a scalar. Hence, it would stand to reason that we can restore the density by integrating over all phase spaces. So ρ would be the integral from 0 to infinity of ρ tilde dv. Now, integrating to infinity here is not necessary, since we'll later cap the velocity to the speed limit so as to avoid having a generalized integral here. Hence, to take the mean velocity, we calculate the average. So v would be the integral of v times ρ tilde from 0 to infinity over the integral of ρ tilde from 0 to infinity. Now this formula, although scary looking, is nothing but an average, which is obtained by taking each velocity v, multiplying it by its frequency, in this case it would be the density of the cars moving at the velocity v, and divide by the total frequency, so that's the total density, which corresponds to the integral of ρ tilde. If you're still not convinced that this represents an average, notice that the formula for the mean velocity looks very similar to the formula of the expected value of some positive continuous random variable. If we replace the density in phase space by the probability density function of the random variable and v by x, then this whole quotient becomes the integral of x times f of x over the integral of f of x. The integral in the denominator evaluates to 1 since it's the integral of the probability density function and it's always 1, and so we get our expected value. This should give us more confidence that this does indeed correspond to an average velocity. From what we have established before, we have that the fundamental relation holds for any fixed velocity. So that would say q tilde is equal to rho tilde times v. And so we may integrate along the positive real numbers to get that the flux is equal to the integral of rho tilde times v. From the mean velocity formula we have established just now, the right-hand side of this equation can be rewritten as the velocity times the integral of the phase density. But the phase density integrated from 0 to infinity is nothing but the density. So we get that the flux at any point xt is equal to the velocity at that point times the density, and this establishes the fundamental equation. The dependence of all our quantities on a temporal and a spatial dimension, both being completely independent of each other, naturally leads to the involvement of partial derivatives in the modeling process whenever we want to examine the change with respect to any of these variables. And therefore, we're going to deal with several notions from multivariable calculus throughout this video. If you're not familiar with calculus and multivariable calculus and wish to learn about these concepts, then this video's sponsor, Brilliant, has got you covered. Brilliant is a multi-platform learning app that focuses on learning by doing. Its lessons are highly interactive and are designed to guide you towards analyzing problems, identifying patterns, and finding solutions on your own, making you a better thinker and a competent problem solver. You won't simply be memorizing concepts to pass your courses, you'll be equipped with reasoning skills to actually do something with that knowledge and conquer real-world problems. Brilliant offers many courses in mathematics, computer science, data analysis, and artificial intelligence, all crafted by award-winning experts from Stanford, MIT, Microsoft, Google, and more. Their calculus and multivariable calculus lessons in particular cover the fundamental notions featured in this video in a beautiful and easy to understand manner, helping you visualize and digest these concepts and build a strong intuition. These lessons capture the most useful and applicable math concepts, allowing you to learn in the most efficient way. We like Brilliant because its bite-sized lessons make learning possible even if you're pressed for time. And its streak system helps you keep track of your goals, make progress every day, and build your habit of learning. They've got something for everyone, no matter if you're a beginner or an expert. So don't miss out on the opportunity. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/mathverseanimated or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. Thanks once again to Brilliant for sponsoring this video. Earlier we've made the assumption that cars cannot exit the road except from the endpoints. In other words, the change in the number of cars is completely determined by the difference between the number of cars entering and the number of cars leaving the road. This is similar to the study of gas dynamics where we assume that matter can neither be created nor destroyed. We now seek to translate this qualitative statement into a sharp mathematical statement. In other words, we want an equation that describes this fact. Recall that the total number of cars on the road segment is n of t, which is the integral of rho from a to b. So to get the change in the number of cars, we differentiate both sides with respect to time. If we assume that the density function is piecewise continuous on ab times 0 infinity, and that the density is not only differentiable with respect to the time, that means the partial derivative of rho with respect to t exists, but also that the partial derivative is continuous on ab times 0 infinity, then we can switch the order of differentiation and integration. But of course, as the density depends on two variables, the differentiation changes from ordinary to partial differentiation. On the other hand, from our assumption, the change is determined by the difference in cars entering and exiting the road, and so the rate of change of the number of cars is going to be the rate of entry at A minus the rate of exit at B. But the right-hand side is nothing but the difference of flux between A and B. Thus it may be rewritten as dn over dt is equal to qat minus qbt. Now it's going to be convenient if we switch the two terms, so we would get a minus sign on the outside. Notice that the difference inside the parentheses can be rewritten as an integral, again by employing the fundamental theorem of calculus. It follows that these two integrals are equal, so we can just simplify further and we get that the integral from a to b of the partial derivative of rho with respect to t plus the partial derivative of q with respect to x dx is 0. A perk of assuming that our functions are piecewise continuous is the ability to apply the Dubois-Reymond lemma, which tells us that the integrand is 0. We're not going to delve into undue pedantry to justify this result, as it relates to measure theory, more precisely the calculus of variations, which is way beyond the scope of this video. For now, let's just accept that this holds, just to proceed. Let's compactify the notation a tiny bit. We'll replace the partial derivative symbol with a subscript containing the variable of partial differentiation. So del rho over del t would be denoted rho sub t, and del q over del x will be denoted q sub x. The equation we're left with is called the conservation equation. So we've successfully transformed the earlier qualitative statement that the number of cars is preserved into a first-order partial differential equation. Now recall from the fundamental equation that the flux is equal to the density times the velocity, so we can replace q here in the partial differential equation with rho times v. This is good progress so far. We've managed to extract a partial differential equation from the model we constructed above. The problem now is there's no way to proceed. If we examine this equation, we can notice that it involves two seemingly independent functions, those being the density and the velocity. This is like trying to solve an equation of two unknowns, which is impossible. In order to proceed, we must make yet another simplifying assumption. We will assume that the velocity is a decreasing function of the density, so v would be v of rho. This is a very natural assumption to make as it aligns with our intuition. If there are few cars on the road, then on average the distance between cars is relatively large and drivers have more leeway to increase their speed. The opposite happens when there are a lot of cars on the road. Drivers cannot drive as fast due to the road being cramped, so to speak. This assumption basically translates the phrase, the denser the traffic, the slower you can drive, in mathematical terms, and it's quite consistent with experience. For this to hold, we demand that the derivative of v with respect to rho be negative. Notice that this assumption also makes the flux a decreasing function of the density. Going back to our partial differential equation, we can now apply the chain rule on the rightmost term to get the following form. So the equation becomes rho sub t plus q prime of rho, which is the derivative of the flux with respect to rho, times rho sub x, which is equal to 0. This is the final, most expressive form of the conservation equation, called the continuity equation. This is a very special form, in fact. In the field of partial differential equations, mathematicians have made several classifications. One of the most elementary classifications are quasi-linear partial differential equations. Just from the name alone, we expect there to be some sort of linearity at play here, and indeed there is. Consider a general form first-order partial differential equation of some function u, depending on two variables x and y. U is the function we want to solve for, which depends on the two variables x and y. This equation is said to be quasi-linear if the highest order partial derivatives appear as linear terms. So this means the partial differential equation would be expressed in a form similar to this. Now we can see where the linearity comes from. This equation looks almost identical to the equation of a straight line. The difference is the coefficients here are functions of the independent variables x and y and all the lower order partial derivatives. Of course, again, in our case, since we have a first order partial differential equation, it would be just u. So a, b and c would be functions of x, y and u, the function itself. So to summarize, a first-order partial differential equation is quasi-linear if it is linear in terms of its partial derivatives. To make the picture clearer, the following partial differential equation is not quasi-linear. This is because the partial derivative with respect to y is squared, hence it's not linear. Going back to our continuity equation, it's very clear that it is quasi-linear. If we replace y with t, take a to be the constant function 1, b to be q prime of rho, which is still a function of x and t, and c to be the constant function 0, we see that it fits the form of a quasi-linear partial differential equation. Our equation falling into such a classification is very advantageous, as it allows us to apply a very powerful method for solving partial differential equations, the method of characteristics. One of the most popular resolution methods for first-order quasi-linear partial differential equations is the method of characteristics. The method of characteristics is attributed to many mathematicians who were active during the 18th and 19th century. The one I find most interesting is Hamilton's attribution. It is claimed that he developed the method of characteristics in the middle of the 19th century during his investigations of the propagation of light. His research eventually led him to introduce the notion of iconal functions and iconal equations, the latter of which can be solved by integrating along special curves he called characteristics. Although there are generalizations of the method of characteristics for fully nonlinear partial differential equations, and those would be more suitable to employ, like the Charpit-Lagrange method, we will only be considering the usual method of characteristics for this video. The derivation of the method of characteristics is a beautiful construction that involves several notions from multivariable calculus, differential geometry, and linear algebra. I'm not going to provide such a derivation not only because it would take way too long, but also because the method of characteristics is often used to provide an explicit analytic solution of quasi-linear partial differential equations. This is all nice in theory, however, often when modeling real-life phenomena, such a privilege is rarely present, so there is no need to plunge into the meticulous computations. Instead, what I aim to use the method of characteristics for is to provide a powerful tool for analyzing the solution qualitatively. If you would like to see a video deriving the method of characteristics, let me know in the comments below. I will, however, be providing a heuristic that should give us a good idea of how this method works. The main idea of the method of characteristics is based on knitting the solution surface using a family of curves, sort of like a blanket. Along these curves, the partial differential equation can be re-expressed as a system of ordinary differential equations, greatly simplifying the problem, at least along some curves. Let's consider a first-order general form quasi-linear partial differential equation. So that would be AUX plus BUY equals C. Of course, A, B, C are functions of x, y, and u. Let's take C to the other side of the equation. The key observation here is that the equation is nothing but the Euclidean dot product of the vectors ABC and UX, UY minus 1. Now, recall from multivariable calculus that the gradient of f at the point xyu is normal to the solution surface at the point xyu. Now, since f of xyu can be written as u minus z, it follows that the gradient is given by ux times uy times minus 1. It's just obtained by differentiating with respect to each variable. So this would entail that the vector ABC is tangent to the solution surface. To reiterate, the plot of z equals uxy defines a surface whose normal at any given point is the vector ux uy minus 1, and the vector ABC is tangent to the solution surface at that point. In order to knit the solution surface, we need a thread to start this process. This is given in the form of an initial condition accompanying the partial differential equation, so it would be u of x0 is equal to some function g of x. This is a curve in the ux plane. As ABC is always tangent to the solution surface at some fixed point, we will use this vector to generate a curve on the solution surface. This curve is called a characteristic curve of the partial differential equation. By going through the entire family of tangent vectors, we will get all the characteristics curve, which will create a full description of the solution surface of U. Let's work with something more symbolic. Let us represent the characteristic curves parametrically as follows. The R parameter is used to represent how far along the characteristic curve we are. This is the main parameter that governs the evolution of the solution, restricted to the characteristic curves, of course. The S parameter specifies which characteristic curve we're on. It turns out that there is no explicit dependence on the parameter S. It, in fact, does not play a significant role in our study, so we'll just ignore it. All you must know right now is that for s equals 0, we get the parametrization of the initial curve g of x. For each point xy, we can make two observations. The vector ABC is tangent to the solution surface z equals u, and on the other hand, the tangent to the curve is partial derivatives with respect to r to each component. but since we're just ignoring the parameter s, we will change these partial derivatives into ordinary ones. These two tangent vectors are different in general, but we can always reparameterize the curve in such a way that we have equality of vectors. The solution of this system of equations gives us analytically the characteristic curves that we seek. We're now going to apply the method of characteristics on our problem. Recall that we require two things for the method of characteristics: the partial differential equation and an initial condition. We already have got our partial differential equation as the continuity equation. So let rho of x0 be the initial distribution of the density function, which we'll denote by rho sub 0 of x. This represents the placement of cars along the road when t equals 0. Since we're studying the evolution of traffic as time progresses, we'll take t to be the parameter of our characteristic curves. Our aim is to find the curves along which the partial differential equation becomes an ordinary differential equation. So let x of t be such a pre-described curve. Note that x of t is a family of positions parameterized by t. Let's analyze what happens to rho restricted to this curve, i.e. rho of xt t. A good place to start is to examine the change of the density with respect to time. So let's differentiate rho of xt t with respect to t. This gives us, using the chain rule, that the derivative of rho restricted to the curve with respect to t is equal to dx over dt times rho sub x plus rho sub t. By identification, the curves that will ensure what we want are the ones satisfying dx over dt is equal to q prime of rho and d rho over dt is equal to 0. But didn't our system earlier have three equations? Well, we only get two equations because we chose the characteristic curves' parameter to be time itself, so the third equation is just dt over dt, which is redundant. But this isn't a big problem. This will not have a big effect on our study. From these equations, we can extract a few facts before even attempting to solve them. First, along the characteristics, the density must be constant. This comes from the second equation, d rho over dt is equal to 0. So let the value of the characteristic along this curve be c sub 0, some constant. Here, x0 is just some point along the road. It then follows that dx over dt is yet another constant. Integrating this last equation shows us that the characteristic curves are straight lines in the xt plane, given by the equation xt is equal to q prime of rho of x00 times t plus x0. So from now on, we will call the characteristic curves characteristic lines. The image here is actually flipped, since x is supposed to be a function of t, so it should look like this instead. However, we will still use this form as the picture of how characteristics relate to qualitative behavior of the solution is much clearer, as we'll see later. So at every point of the road, we have a characteristic emanating from that point. Although as mentioned before, we are not going to be explicitly solving for the density function, we will be using the characteristics we just found to understand how such a function evolves over time. This is because characteristics are seen as directions along which information propagates. So in the context of traffic flow, this would be some sort of change in the density function. An observation we can make here by virtue of the characteristics being straight lines is that the density at any point xt in spacetime can be written implicitly using the initial density distribution as follows. This is because the solution at xt is the same as x minus q prime rho of xtt 0. So even though we don't have an explicit solution, we still get an implicit solution. Before we see how we can use characteristics to analyze the evolution of density, we will have to further delineate the relationship between the velocity and density. We have to do this because the slopes of the characteristic lines depend on the values of the derivative of the flux, where this former's behavior is ambiguous, which makes the studying of the behavior of traffic very tedious unless we give a well-defined expression to the velocity, which will in turn give us an expression for the flux. This is the modeling part of the problem, as changing the type of relation we use to describe the velocity changes the description of traffic. Recall earlier that we've made the assumption that denser traffic leads to slower driving. If you follow this assumption to its extremes, then we expect that for no traffic, that is, no cars on the road, the cars can travel as fast as the drivers want. Let's cap that speed to some value, say v sub max. This reflects theoretically the speed limit. Practically, however, that's another story. On the other extreme, we expect there to be a maximum traffic density, say rho max, past which the cars can no longer move. This reflects the situation where cars are situated bumper to bumper. In other words, it's a traffic jam. To summarize, we've got the following two conditions. The velocity when there's no density is the maximum velocity, and the velocity at maximum density is 0. If we were to graph the velocity function with respect to the density, we have these 2 points that serve as our anchor points. The question now is, in what fashion should we connect these points to each other? There are many ways to do this, in fact, infinitely many ways, but what is the best way to do so? If we were writing perhaps a research paper about traffic flow, the answer would probably be to construct the graph based on empirical data, so we'd analyze the behavior of traffic velocity along a whole lot of roads and construct an appropriate curve from the data collected. This would probably lead to more realistic models, which would help make more precise predictions. For pedagogical purposes, I'm opting to go with the simplest interpolation, the linear one. So we'll just connect these 2 points with a straight line segment. The equation of such a line segment is as follows. You can try and plug the values at 0 and rho max to see that this corresponds. This equation of the velocity gives us explicit relations for the flux and its derivative with respect to density. Q of rho is obtained using the fundamental equation, and Q prime of rho is just the derivative of Q. Let's take a moment to see if this matches the intuition we have. When the road is empty, or when there's a traffic jam, there is no net movement on the road, so we would expect the total flux to be 0. These 2 situations precisely correspond to the roots of the expression we have above, as Q vanishes when rho is 0 or rho max. We can also find, as per this model, the optimal traffic density for maximum traffic flow rate. This would correspond to half the maximum density. So, at half maximum density, the flow of the cars is maximized. The graph of the derivative of the flux is a straight line. This shows us that the derivative of the flux is a decreasing function, as expected, which is precisely the information we need to start our analysis, as you'll see. Let's now see how we can compare between different traffic densities using the characteristic lines. Let's consider 2 points along the road, say x0 and x1, where x0 lies before x1. So mathematically this would mean that x0 is less than x1. Let's suppose that the initial density at x0 is larger than the initial density at x1. So we've got heavy traffic heading to light traffic. Mathematically, this would mean that rho 0 of x0 is larger than rho 0 of x1. Since Q prime is a decreasing function of rho, then applying it to both sides reverses the inequality. This tells us that the characteristic emanating from x1 is steeper than the characteristic emanating from x0. Do not be alarmed that this doesn't match our picture. Recall once more that here x is a function of t, so the axis should be flipped, and this adjusts to this discrepancy. Judging by how the characteristics are pointing, we see that the traffic at x1 is moving faster than the traffic at x0. The fanning out of these 2 lines indicates that, as time progresses, a gradual separation between the 2 traffic masses at x0 and x1 forms, which falls well within how we expect the traffic to behave in this situation. Let's examine a more general situation of heavy traffic heading into light traffic. Let's consider some initial density distribution, and mark 3 points along the road. At point A, the leftmost point, the road is at maximum traffic density. At point B, the center point, the road is at half the maximum density. And at point C, the rightmost point, there is no traffic, so the density is 0. These points are important because they are the points where we know the values of Q prime. Furthermore, due to these points lying within the extremities of the density distribution, all changes that happen to the other points will lie somewhere in between these values. Let's get to calculating the slopes and drawing the characteristics. I'll skip the unnecessary details. The slope at each point is the following. At point A, it's minus Vmax, at point B, it's 0, and at point C, it's Vmax. And so if we were to plot the characteristics, they would look like this. Now, let's use these characteristics to see what happens to each point one by one as time progresses, say by t hours, starting by the point A. So the characteristic emanating from the x-coordinate of A, xa, has the following equation. So after t hours, the corresponding point along the characteristic is going to be x of t, which is going to be minus v max t plus xa. This is going to be the x-coordinate of the peak, aka the point A, after t hours have passed. But since the density is constant along the characteristics, the y-coordinate of A will remain unchanged. So the fate of the point A after t hours is to be translated to the left by a factor of minus v max times t. Notice that this translation factor is completely determined by time and the characteristic itself. The negative sign matches the characteristic pointing to the left, and the magnitude v max of the translation is the slope of the characteristic. Let's examine the point B. Doing the same work as we did for A and determining the characteristic, we get that x of t is equal to b. You can see it is but a line pointing upwards, and the x-coordinate of b remains unchanged. Again, since the density is constant along characteristics, the y-coordinate of b also remains unchanged. This shows us that the point B remains stationary. For the point C, doing the same work again, skipping the details yada yada, we get similar results to A. The point C, as per the characteristic x of t is equal to v max t plus x sub c, is translated to the right by a factor of v max times t, matching the behavior of the characteristics. So this is the evolution of the density distribution after t hours. The initial graph gets stretched out about the point B, completely and beautifully matching the characteristics. This is cool and all, but does this match how we expect the traffic to behave? Let's conduct a sanity check. A quick remark though. Since the behavior of the cars left to C and right to A might affect how the traffic behaves at those points, we shall ignore those regions and restrict the road to whatever lies between XA and XC. Since the density at C is much smaller than the density at B, the cars near C move much faster than the cars near B. If we assume no cars are ahead of C, then this region of emptiness, that is, no density, in front of the cars near C will propagate rightward, pulling away from the cars to the left. Now, the cars in front of B will migrate to the lower density region to the right, decreasing the density near B. However, this drop in density will be compensated by the upcoming traffic from A. So there is no net change in density near B. Finally, the movement of cars right to A towards B will decrease the density near A, but if we assume that there are cars behind A, those cars will eventually catch up to this peak in density, keeping this region of high density alive. This peak moves backwards in space, indicated by the direction the characteristic points to. So here comes the main conclusion. The characteristics reveal the direction of motion of density points and not the cars themselves. Let's examine a situation from real life. Suppose that we've got a bunch of cars lined up behind a red light. This initial density distribution can be described as follows. If we put the red light at x equals 0, then left to this red light, which would be x negative, we would have rho max, and right to this red light, we would have 0. So the initial density is this piecewise function. Let's assume that at t equals 0, the light turns green and the cars are allowed to move. Let's study the evolution of traffic. The first thing we do is plot the characteristic lines. This is very easy to determine for this specific distribution. For x larger than 0, the characteristic lines have slope q prime of 0, which is v max, along which the value of the density stays 0. And for x negative, the slope of the characteristics lines is q prime of rho max, which is minus v max, along which the density keeps the value of rho max. Since this is technically a situation of heavy traffic heading into light traffic, the same reasoning we've applied to the general situation can be applied here. Only this time, instead of only one point corresponding to a maximum density, the entirety of the graph left to the y-axis is at maximum density. So every point therein will be translated to the left by a factor of minus v max times t after t hours. Similarly, for the same reasons, the section of graph right to the y-axis will be translated by a factor of v max times t after t hours. So for any time t, here's how the density looks like. This behavior is consistent with what happens in reality. When the light turns green, the first car in the front is free to move at theoretically max speed Vmax. If we ignore the time taken for the car to accelerate to such velocity, then after t seconds, its position will be Vmax times t, pushing the region of zero density rightward. Due to human error, the second car will not immediately move after the first car, causing a delay which will propagate leftward, described by the characteristics pointing to the left. More precisely, if a car is a kilometers away from zero, i.e. its position is x minus a, then the car will be sitting still for some time before it can move, precisely until the boundary of the leftward moving region, x equals minus vmax times t, catches up. Solving for time, we get that the car will start moving after a over vmax hours. The apparent issue now is that we don't know how the density is distributed between the values minus vmax times t and vmax times t. The issue comes from the discontinuity of the initial distribution at 0, and is further visible by the behavior of the characteristic lines at 0, as they point away from each other. The distance between the points on each characteristic becomes larger and larger as time progresses. Consequently, the gap in the density function grows larger and larger as time passes. The analysis of the real-life scenario we did earlier should give us an idea on how to amend this issue. A gradual build-up in velocity encourages us to conduct some sort of interpolation connecting the two lines. The characteristic diagram further supports this. This gap is just begging to be connected with characteristic lines emanating from 0, gradually turning from left to right, producing a fan-like shape. Let's find a formula for these lines. As these supposed fan-like characteristics all emanate from 0, then their equations are all of the form xt equals q prime of rho times t. The trick here is to solve for rho. We finally get this formula for rho, which is precisely the equation of a straight line segment connecting the two disjoint graph sections. This linear interpolation is unique to this model. If we change the relationship between the velocity and density to a non-linear one, then we might get different results. The cases we've analyzed above all involve dense traffic moving into lighter traffic, which I think most people would agree is a mundane situation, as little risk is involved. So let us consider a more intriguing and risky opposite case, that is, when light traffic heads to heavier traffic. Let's start with the most simple case, and consider 2 points x0 and x1 just like before. Let's assume that the traffic at x0 is less dense than the traffic at x1. Follow the calculations just like we did before. We see that q prime of rho 0 of x0 is larger than q prime of rho 0 of x1. So this time the characteristic emanating from x0 is steeper than the one emanating from x1. Observe that at some point in time the two characteristics will eventually meet. This is not a good thing. Recall that the density is constant along each characteristic. That is, it assumes some constant value along the first characteristic and a second distinct value along the second characteristic. I think you see the problem now. Since these two lines meet, this indicates that the density must assume two different values at once. In other words, this means that the density is multi-valued. Before attempting to solve this issue mathematically, we've seen that often the expected behavior of traffic in real life gives us inspiration for finding the necessary steps and assumptions that allow us not only to proceed with the problem, but make consistent generalizations. So let's do that. If the traffic at x1 moves slower than the traffic at x0, eventually the traffic at x0 will catch up to the traffic at x1. But since in this model cars are not allowed to pass each other, then the rear cars are forced to slow down, causing a sort of wave to form that propagates backwards. We will explain this behavior in more detail, but to better illustrate this point, let's consider a more expressive example. Let's consider this initial traffic distribution. So just like before, rho 0 is piecewise defined. This time left to the y-axis we've got some density rho 1, and right to the y-axis we've got another density rho 2, which is larger than rho 1. This is another situation of light traffic heading to heavier traffic, perhaps a simple one, so let's study the evolution of this situation. I think you get the gist of things now. We find the characteristics and plot them. For x negative we get a slope of q prime of rho 1, and for x positive we get a slope of q prime of rho 2. And as the derivative of the flux q prime is a decreasing function of the density, it follows that q prime of rho 1 is larger than q prime of rho 2. Now we can distinguish three cases from this inequality. The first is when both slopes are positive. The second is when q prime of rho 1 is positive and q prime of rho 2 is negative. And the third is when they're both negative. So let's examine what happens case by case. The first case happens when rho 1 and rho 2 are both larger than rho max over 2. Indeed, this follows quickly from the equation of Q prime. This tells us that the slopes of the characteristics are positive, but since Q prime of rho 1 is larger than Q prime of rho 2, these characteristics will most definitely intersect at some point. The velocity of traffic at the lower density region is v of rho 1, and the velocity of traffic in the higher density region is v of rho 2. And since the velocity is a decreasing function of rho, we've got that v of rho 1 is larger than v of rho 2. We can find the translation factors of the graphs after t hours just like we did before. The rear of the high density region will have moved rightward by a factor of v rho 2 times t, and the front of the low density region would have moved rightward by a factor of v rho 1 times t. But as v rho 1 times t is larger than v rho 2 times t, these graphs will stack on top of each other, specifically for x between these two translation factors, conveying the multi-valued behavior we've talked about earlier. It's very tempting to just cut off one of the extra parts to get rid of this problem, and this is indeed the solution we're going to employ. By allowing the density function to have a discontinuity, we fix the multi-valued problem. However, unlike with the earlier case of heavy traffic moving into light traffic, this discontinuity will move as time progresses. Such a move in discontinuity is called a shock wave, or simply a shock. We will discuss what shock waves correspond to qualitatively, but first, we must build a method that allows us to determine the velocity of the shock, whose position will denote by x sub s for every time t. Once more, we need a couple of assumptions in order to proceed. The first is that the quasi-linear continuity equation must be satisfied at both sides of this shock position. This will assure us that we can always build the characteristics around the shock. The second is that the net flux Q must be conserved at both sides of the shock wave, meaning that the rate of cars passing by the right side of the shock wave is the same as the rate of cars passing by its left side. The significance of this second assumption is that it allows us to relate the velocity of the moving shock wave to the flux left and right to the shock wave's position. This probably makes little to no sense, so let's write down some stuff. Let's denote the shock velocity by xs prime. The relation we're about to derive is called the Rankine-Hugoniot condition, which comes from the field of fluid dynamics. It's used to describe the propagation of a shock wave based off the information from both sides of the shock. For this video, I will only be using the Rankine-Hugoniot condition for computational purposes only, to simplify calculations. That's why I'll refrain from explaining the semantics of how it works. However, I will be providing a derivation of this formula, but keeping the calculations loose. The Rankine-Hugoniot condition starts from the conservation equation. Let xl be some point left to the shock and xr be some point right to the shock. So xs is in the interval xl and xr. We're going to integrate along this interval passing by the discontinuity. So let's split the integrals. Via the fundamental theorem of calculus, we can exchange the order of integration and differentiation on the left term. The right term is going to be the difference in flux before and after the shock wave. We'll now split the remaining integral at the shock wave. We can simplify this derivative by using the Leibniz integration rule. Just a quick pause here. Since we're left of the shock, then we will be taking the value of rho from left, which would correspond to this. Formally, this step would be justified using limits, but just trust me that we can do this. Of course, as xl and xr are constants, their derivatives are 0, so we're left with this. Rearranging some terms, we get ourselves the formula we're looking for. Notice that if there is no discontinuity in the density function rho, then there is no discontinuity in Q either. This turns the Rankine-Hugoniot condition to just the ordinary derivative of Q with respect to rho, and so the velocity of the shock is just Q prime of rho. Integrating with respect to t, we get the shock position visibly matching the form of a characteristic line. Here x0 is just some constant. So the shock condition in case of no discontinuity just corresponds to a characteristic. This resonance with the continuous case should give us confidence that this is an appropriate generalization. So to go back to our problem, the shock wave will transport the initial discontinuity in rho with a velocity xs prime, and according to the characteristics, such a shock will have characteristic lines to its left of slope q prime of rho 1 and to its right of slope q prime of rho 2. Applying this for all time instances, we get the following picture. The middle line here separating the two characteristic regions is representative of the shock wave. As we would expect, its slope is proportional to xs prime. In general, this has no reason to be a straight line. Remember that this slope changes with time. But this nice behavior is a perk of choosing the linear model, as we'll see later. This constant slope indicates that the shock moves at a uniform velocity, and it, pointed to the right, tells us that the shock wave formed moves rightward. If we interpret the shock as a disturbance in traffic flow, then this behavior is not problematic, as this disturbance is moving rightward away from the incoming cars. For any time t, the density function can be obtained from the above sketch. It perfectly describes the shifting of the initial graph leftward. Let's try and determine the velocity of the moving shock. Going back to the Rankine-Hugoniot condition, we can plug the explicit formulas of the flux and density. Simplifying this whole thing leaves us with the velocity of the shock is equal to q prime of ρ1 plus ρ2 over 2. We get the very satisfying result that the velocity of the shock wave corresponds to the average of the two densities left and right to the discontinuity, and the slope of the shock is bounded by the slopes of the two characteristic regions. This in fact is unique to the linear model, but what holds consistently in general across all models is the following bound, which follows from the fact that q prime is a decreasing function of the density. This is called Oleinik's entropy condition. For the second case, we can just apply everything we've derived in the first case. This time we have that ρ2 is larger than ρ max over 2, meaning that q prime of ρ2 is negative, i.e. the slopes of the characteristics right to the initial discontinuity point backwards. Remark that if, in absolute value, q prime of ρ1 is larger than q prime of ρ2, then we still get that the shock wave line points rightward, so the shock still propagates forward away from the incoming traffic. Case 2 now behaves very similarly to case 1, with the front cars just moving slower. The more interesting and extreme case is case 3. This time we require that ρ1 and ρ2 be both larger than ρ max over 2, so both slopes here would be negative. From Oleinik's entropy condition, we clearly see that this time the shock moves backward. This is because its slope is negative. This is a potentially dangerous situation. Depending on the velocity of the shock and the magnitude of discontinuity on both sides of the shock, a huge oncoming shock wave may be heading towards the incoming drivers at the rear, which are moving at relatively high velocities, and they are none the wiser. These shock waves, along with human error and inattention, can potentially lead to serious accidents. This is why these types of backward moving shock waves are a great safety concern in traffic engineering. Transportation agencies seek to minimize the frequency of occurrence of shock waves. There are many techniques that mathematicians and engineers have developed to study the effects of shock waves on traffic, some theoretical in nature, and some more practical, but I think the video has gone on long enough.
I hope you've enjoyed this video and found it insightful. I initially planned for this video to be much bigger and to be of higher quality, but due to my computer's limitations, I faced a lot of issues during the rendering process and it crashed a lot when editing the video, so the video ended up being a bit rushed and it didn't meet the standards of quality that I hoped it would meet, so I apologize for the drop in quality in this video. But in any case, I want to thank One Small Brilliant for sponsoring this video, and if you've noticed an improvement in audio quality, then that would be thanks to my amazing classmate who has provided me with a professional microphone. I want to personally thank you, you are an amazing person. And finally, I want to thank you guys for all of your support. Engaging with you and reading your comments and hearing feedback from you is genuinely enjoyable for me, so I would like to thank you so much for helping populate this channel. Okay, so this has been a little bit of a rant. I hope you've enjoyed the video and see you in the next one.